Okay. Good afternoon, everyone. So a few announcements before I start the lecture. Quiz 7 has been posted. Hopefully you received the email. And the deadline for that quiz is going to be Monday, the coming Monday on 11 a.m. Eastern Time. The grades for quiz 6 will be released hopefully soon after the end of this lecture. And then there will be just one quiz next week, which will hopefully release on Monday. As you probably have seen the announcement, the deadline for lab 4 was extended to Friday. Not only the day has changed, the timing also has changed. Instead of 8:30 p.m. now it's 11:30 p.m. Eastern Time. The other announcement that I posted online was about the way we're going to calculate the 30% of your final grade, which is related to your quizzes. We've decided to just exclude your 5 lowest grades. That should help everyone with their grades, hopefully. Okay, so if there are no questions, then I'm gonna start the lecture. Okay, so we were talking about caches. Now we talked about direct set associative and fully associative caches. Now let's look at an example, see if having a bigger cache is always good. So yeah, let's assume that you have a 2 megabyte cache and it's 8-way set associative. And let's assume that your physical pages are 4 kilobyte. Now, suppose that the hardware is using the lowest low order bits of physical address to index the cache. And let's assume, for whatever reason, the operating system has allocated a process, let's call that process A, physical pages that are exactly separated from each other by 256 kilobytes. So I have, let's say, starting at address X, I have one page for process A, then I add 256 kilobyte to the end of that to get to the beginning of that address to get the address for the next page that is allocated to A. So what happens in this scenario? How effectively process A is going to consume the cache that we have? So if you do the math, if you have a 2 megabyte memory with 8-way set associative cache, then you'll realize that, and then if you're using the lowest bits of your physical address, you'll see that every block or every byte in memory, every 2 blocks in memory that are separated from each other by 256 kilobyte will be mapped to the same cache set. So in essence, when all the pages allocated to process A are separated by the same stride, what happens is that all of those pages will be mapped to the same set. Now, if you have a 2 megabyte and cache, which is 8-way set associative, then you have 8 blocks within each set that that can hold your data. So every page will be mapped to the same set, and every set is an 8-way set. So at most, you can keep 32 kilobyte of data associated to process A, because after that, every incoming page will have to evict another page, because all of them are mapped to the same set, and this set has only 8 ways. So basically, they're going to just compete for those 8, and once it's full, they're going to evict each other. So in essence, from this 2 megabyte cache, process A is only using 32 kilobyte of it, which is basically only 2% of the cache. And this is very disappointing. We have a 2 megabyte cache, but we're effectively only using 32 kilobyte of it. The way operating systems avoid this from happening is by using a method that is called page coloring. What it does is basically it associates a color with all the pages that are mapped to the same set. So all the pages that are mapped to the same set in physical memory are going to get the same color. Now, when the operating system wants to allocate or do the address translation, allocating physical memory to each process, it tries its best to allocate pages with different colors to consecutive virtual pages. So if you have virtual pages consecutively in the address space of a process, and you want to find physical pages for these, what you would do is you just try to find different colors, because these different colors would mean that these physical pages would be mapped to different sets, and they wouldn't be competing against each other. Okay, now that we're here and we saw one instance of ineffective use of cache, let's talk more generally about what would be the cause of having cache misses. So just a reminder, cache hit means that you access your cache and then you find your data, and cache miss means that you access your cache and your data is not there. So the first reason for not finding your data is a compulsory miss, which means that it's just a cold start. This is the first time you're accessing this address, so it's not cached. And a cold fact about this cold miss is that you can't really do anything about it, almost. So if this is the first time you're seeing this address, you probably hadn't had any chances to cache it before. The other one that you might have is capacity misses. So basically what this means is that the number of blocks inside your cache are less than what your program needs. So they're going to just evict each other, very similar to the situation that we talked about. So with capacity cache, you can actually increase your cache size, right? Let's say you have a 2 megabyte cache, and you actually need 3 megabyte cache to, fit in all your data inside your cache. then well, the solution is easy. Just increase the size of your cache if you care about cache misses. Of course, increasing the cache capacity means you're going to have a higher heat time, which we talked about last time. Then we have the conflict misses. So with conflict misses, the same. So the best example is a direct map cache, where a bunch of memory blocks are exactly mapped to the same cache block. So every time you want to cache one of those, you're going to evict the previously cached one. The solution to this one is to increase your cache size as like the capacity. So if you have more, then less memory blocks would be mapped to the same cache block. So the probability of conflict goes down. The other thing that you can do is to increase the associativity of your cache. So with direct map cache, every memory block is mapped to the same cache block. If you have a two-way set associative or four-way set associative, then you have some flexibility, because even though they're all set all those memory blocks are mapped to the same set, there are 4 different options in that set that could be used. So the probability of conflict goes down. I got a question. What's the problem with having multiple memory locations mapped to the same cache location? Well, there is so there is no problem per se. That's the nature of it, because the cache is in essence is smaller than memory, so there is no way around it. You have to map multiple locations. Now the question is, do I want all those locations to be mapped to the same set, or do I want to map them to the same cache block? So if all of them are matched to the same cache block, then I have a direct map cache. Basically, every one of them would compete for the same block. Now, if I have a set associative cache, then all those would be mapped to the same set, not same blocks. So within the set, you have multiple blocks that you can use for them, right? So they wouldn't necessarily evict each other, unless you know you're accessing, let's say, 8 blocks, and then you have a 4-way set associative cache, and all those blocks are mapped to the same set. Then, well, you have 4 blocks inside your set, and you're accessing 8 blocks, so they're going to compete, and then they're going to evict each other. Okay, and then lastly, there is the coherence misses, which we sort of talked about previously. These are the misses that happened because of the cache coherence protocol. So because of the invariance that your cache coherence protocol wants to have, it basically evicts some of the blocks to make sure that the cache is coherent. And when a block gets evicted, then you're going to have a miss there. Okay, so now that we talked about that, so eviction happens. What should we do? Which cache block should we use to evict? Now that's a question. So easy answer, if you have a direct map cache, is that you don't have any other choices, right? Because your memory block is mapped to the same cache block, you have to evict whatever you have cached in that block. So you don't need to choose between different options. You only have one option. So you evict the one that is already cached. Now, what about set associative caches? So let's say I have a two-way set associative cache or four-way set associative cache. Now I'm using all 4 blocks inside my set, and I have accessed a new block which is mapped to the same set. What I need to evict one of those 4. Which one should I choose? One answer is, well, randomly choose one of the 4. The other answer is, well, choose the one that was least recently used one. So if you haven't been using that block for a while, then you're most likely not going to use that block in the future, so evict that one, which is LRU. We're going to actually talk about these when we talk about paging, because this issue comes back again when we use our physical memory as a cache for our storage devices. So in that context, we also need to talk about eviction because we don't have enough physical pages to fit in all the virtual pages. So in that context, we're going to evict physical pages to secondary storage system, to our hard disk. So we're going to talk about these in details. We're going to talk about multiple replacement policies. So we'll see more on this later. Now, another issue that we need to add to consider is what happens on writes. On reads, if you have a cache miss, you probably you have to go to the memory, bring the data to the processor, and potentially cache it for the future accesses. Now, what happens with write? So there are different methods or different ways to deal with writes. So the first one is write through. So if you're going to write to an address, what you do is you not only write to that location in your cache, you also write it to your lower level memory. So this is basically your write goes through your memory subsystem and gets basically propagated until it reaches the origin. So what are the good things about this? The good thing about this is that if later on you want to evict this cache block, you don't need to write it back because you've already done that. Bad thing about this is that it could hold the processor hostage while this write is happening. So you want this write through to go and finish before you can go ahead with it. And we all know that it takes more time to go to the secondary and to the second and third and fourth level cache. But with write through, you have to wait for all of them to have the data before you can move on. I got a question. What does it mean for the write to be buffered? Yes. So this actually has. I'm going to give you a high-level answer. This mostly is discussed in computer architecture courses. But what it really means is that because of what I just said, that writing or reading even from second level and third level caches are more expensive because they're further away and you have to, pay a cost. What happens is usually they put a buffer, and so it's basically a bunch of registers that like a queue right after your cache before going to memory. So they're close to the processor, they're closer to the processor than the memory, so it's easier to write in those buffers. And then the memory will just dequeue requests from that buffer. So basically, once you write your data in those buffers, you're assured that your data is going to eventually be written in memory, so you can move on. You don't need to wait until the end. So these are called write buffers. They're still more expensive than just writing in cache because you now have to write in buffer. And the other issue with them is that when the buffer gets full, because memory is slower than the caches, so you might write to those buffers in a higher rate than memory can dequeue from that buffer. So once the buffer is full, then you have to stop. So it just kind of delays when you stop. But if the buffer gets full, then you have to stop. Okay. The other popular method is called write back. So when you're writing, you only write in your cache, write the data to your cache, and you just hold on to this write to be propagated to memory until you want to evict this block. So this is a little bit better in terms of performance of writes because you're not waiting, but then it will just make the reads a little bit expensive in some cases. When you have to replace a dirty block, then you have to wait for it to be written back to the memory. So processor is not held hostage, but then it adds a little bit more complexity. You have to keep track of which blocks are dirty, which blocks have to be written when they're evicted, and it could actually make read misses more expensive because then you have to write your data back to the memory. Okay, so what does read miss? Oh, what does read misses cannot result in writes mean? Yeah, so you might actually be reading from a cache block that is not dirty. So if what you want to evict, so when you have a read miss, so you wanted to read a memory location and you couldn't find it in cache, so you want to bring that now to the cache, and potentially you have to evict a block. Now, depending on which block you're going to evict, you might have to pay the write back cost. So if the block that you pick as a replacement is a dirty block, then you have to write it back to the memory. If the block that you pick is not dirty, then you don't need to do a write back. So basically, this is why it says it may require, depending on what block will be chosen as a replacement. Now we said all of this basically for one specific purpose, and that's basically, I mean, just to remind you, we were talking about address translation, virtual to physical address translation. And if you remember the last slide in address translation, we talked about how expensive it is sometimes to do the address translation. If it is done in software, then it's even more expensive. But if it is done by hardware, you might still have to access like 5 times your memory to translate one address. And then the end conclusion there was, well, we need to cache these translations. And that's why we started talking about caches. So now we're going to see how caches could help us with address translation. So this is just a reminder of how address translation works in a 64-bit system in x86. As you can see, just to translate one address, you have to go through 4 levels of page table, and this is very expensive. So this is the picture that we saw at the beginning of the lecture on caches last time. Now, where are page tables? Well, page tables are in memory, right? This is where we have the page tables. When we, let's say, you have a page table miss, you want to translate it, and then hardware starts doing the page table walk. So you might hear this from me again and again. So a page table walk means when the hardware goes through all these levels of page table to find the translation. Now, what does it really mean to do a page walk? It means to read from memory, because page table is in memory. And when you do that, basically what you're doing is you want to cache, right, all those pages that you translate, all those page table entries that you're translating. So hopefully you want to have a situation where the recently translated memory virtual to physical memory translations are cached very close to the memory, to the core, so that if let's say you're going through an array, and your array is let's say like 10 elements, you don't want to translate the address of the data for all 10 in every iteration that you're working with this array. So if you translate the address for those, you sort of want to keep it somewhere close to the core, so that the next time you want to translate those addresses, you don't have to again go to memory to translate them. So we're going to do this by using a structure, a hardware structure that we're going to call translation lookaside buffer. The abbreviation is TLB. Abbreviation is TLB. So a TLB is going to act like the caches that we've seen, and it's going to keep the recently translated addresses for us very close to the memory, very close to the core. I'm sorry. So if you hit in TLB, so TLB now, whenever I'm talking about TLB is just another cache, right? It's a special purpose cache that we're going to use for address translation. If I hit in TLB, it means that I don't need to walk through my page table. Let's say that 5 times going through my page table to translate. But if I miss in TLB, then I have to actually go through all those. I have to start or initiate my page walk. Now, one question is that, do you always have this locality in address translation? Because if you remember, caches were good if we had data locality. Now let's actually look at that question in more details. Do we have address translation locality when we're working with instruction accesses? Yes. Why? Because it's usually sequential. So you have the spatial locality. If I'm reading PC at this time, I'm potentially reading PC +4 in the next cycle. So you have that sequential access. Therefore, you have spatial locality. Now, if you're working with your stack, if you're then you actually have also a locality in your stack, right? Because all the data in your stack, how big is your stack, right? You keep using your parameters on the stack, so you have temporal locality in those cases. What about data accesses that you have? So with data accesses, sorry, with this I have to elaborate more. So what does it even mean to access your stack? Basically you're translating your stack pointer, right? If you look at the stack, it's usually in one location, right? You let's say you call a function, so all the arguments are pushed on the stack, and the stack pointer is there, right? So every time you want to access your arguments, you basically have some sort of spatial and temporal locality in some cases. So the address is not changing much. With data, it's a little bit tricky. It really depends. One example that I said, if let's say you have an array, then if you translate the address for the first element of the array, you're probably going to translate the address for the second element of the array. You're going to translate the address for the third element of the array. And you might actually have to do this again and again. Let's say you're in a loop working on all elements of your array. So you probably have both temporal and local and spatial locality. But in some cases you don't, right? It's not necessarily the case that you always have this. Okay, so to put everything in, this is now what we're gonna have for address translation. We have our physical memory. We have our page tables. This could be multiple levels of page table. And now we're going to put this cache between our CPU and our page tables. So every time we want to translate a virtual address, we go to TLB. If we hit in TLB, we have the physical page number for our virtual page. So we just use the offset to go to memory right away. If we miss, and then we bring the data. If we miss in TLB, then we're going to go and do the page table walk. If what we want is in page table, if the address is translated and is valid in page table, then you first of all cache it. Second, you use it to go to page to physical memory. And if it is invalid, then you raise an exception. Now, like any other caches, we have to be conscious of consistency problems. So what happens if you have cached a page table entry, a translation, you have cached it. Now, for whatever reason, operating system changes the permission for that PTE, for that page table entry. Let's say it was read write. Now it's just read only that page. So what should happen is that now the TLB entry should be invalidated. What you have cached in TLB is not valid anymore. So in early computers, you didn't have any way to individually work with entities in your TLB, so you would have to flush your entire TLB, whatever you have cached. You would flush it, but modern architectures now allow you to remove individual entries. So you just invalidate that individual page table, TLB entry that corresponds to the page table entry that you have reduced its permissions. What happens if you add permission to a PTE? In that case, you actually don't need to do anything. The reason is when, let's say it was a read, now you have changed that page permissions to read and write. If your process wants to write into that page, the hardware will first go to TLB and sees that, oh, this is just read only. So it will raise an exception. At that point, operating system gets involved. It would remove the TLB, and resume the work. This time again, the process, you start from where you left off. You again access that. This time you don't find it in TLB. You have to now go to page table and just find out that no, it's a read and write, so it's safe. You continue. In cases where you invalidate page table entry, you also need to invalidate your TLB. That should be straightforward. Now let's talk about accessed and dirty bits. If you remember, in the page table entry, we had different bits. One of them was accessed bit, and one was the dirty bit. Remember, these are for the pages, right? Because page table entry is associated with a page, with a physical page. Now, in our TLB, usually we don't keep track of accessed bit. So when hardware for the first time, so let's say the hardware wants to translate a virtual address, it accesses TLB, it cannot find that translation in TLB, it goes to page table, finds it, it's a valid entry, and it has all the accesses, so there is no permission problem. So at this point, I've found the translation. Now, the hardware sets the accessed bit in page table, meaning that, okay, I have accessed this page. We'll see why this is important for the operating system to know which pages have been accessed. I mean, you can think about it right now, because if you remember when I said least recently used policy, we probably want to know which pages have been used recently when we want to evict a page. So this is where the hardware is helping us. Hardware says, okay, I've recently translated this address. It means that I needed to access this page. So I'm going to set this access bit to 1. But note that because we don't have this access bit in our TLB, further accesses would not be reflected. So this access bit sets to 1. Now, next time that your program accesses this page, and hardware finds this memory, this address cached in TLB, it's not going to go back to page table because that would be just wasteful. I already have found the translation in TLB, so the hardware is not going to go to the page table entry. So we will only get a feedback from hardware when the address is not cached in TLB. All the further accesses that get hit in TLB would not be reflected. So hardware is not going to set anything in page table entry. This is very important to note. Okay, we'll talk about it, why it's very important when we talk about paging. What about dirty bit? So unlike accessed bit, TLB actually keeps track of the dirty bit. So every time you write, and let's say you miss in TLB, so you have to do the page table walk, your hardware will set the dirty bit in your page table entry and also the TLB. So both of them will have the dirty bit set to 1. When you hit in TLB, so let's say you're writing to a page and you find the address in TLB, again, page table walk is necessary. This is very, very important. So if, I mean, let me correct myself. If you're writing and you hit in TLB, you look at the dirty bit in TLB. If the dirty bit in TLB is not set, then you have to do the page table walk to set the dirty bit in both TLB and also page table. But if you've already set the dirty bit in your TLB, so if the dirty bit is set in TLB, the hardware doesn't need to go to page table and set the dirty bit because it assumes that it's already set, right? Very important distinction. Okay, I got a question. So just to clarify, the TLB stores the final physical address for a virtual address, right? Or is it the final PTE? It's the virtual page number to physical page number that is translated, because you don't need to translate the offset. Offset we're going to use as is, so we only translate the virtual page number to physical page number. And that is exactly what you have in page table entry. But then there are other things you have in page table entry that you don't necessarily store in your TLB. So what you store is essentially the virtual page to physical page translation. There are, again, a bunch of other information in PTE that you may or may not cache in your TLB. So it will depend on the architecture, which of those bits in page table entry are also stored. So in this slide where I'm talking about here, I basically said that the accessed bit is usually not stored in TLB, whereas it's actually stored in page table entry, but then the dirty bit is stored in both of them. Okay, so what is the benefit of this, having a dirty bit set in TLB? The benefit for this is basically that we're going to save bandwidth from going to page table all the time. Because if we have set the bit in page table in the TLB, then we're sure that the dirty bit is also set in page table, so we don't need to go and do it in page table. And it's very important to set the dirty bit in page table, because that's how we tell the operating system that this page has changed. So if this page has to be evicted, it has to be right back to the disk. So this is very important, right? Which is totally different from access bits, because access bits like only says, oh, I read from this page. It doesn't say anything about this page being dirty or not. Okay, so now the question is, do we really need the dirty bit, both in page table entry and page table and TLB? And the answer, this should be a theme now in this course, that whatever you can do in hardware, you can do it in software as well. So the answer is no, we really don't need to have it. It's not necessary. An operating system can emulate this, which is something that is actually done in BSD Unix. So initially, how can we basically emulate having a dirty bit? We can just mark all our pages as read-only. Even though they have write access, we make them all read-only. Every time something is going to be written to a page that is read-only, the hardware is going to raise an exception, so operating system will get involved, and then you can actually realize that, oh, I'm writing to this page, so you can keep track of it. Again, to remind you, we needed the dirty bit exactly to talk to the operating system, to tell the operating system that this page has been modified. So another way to do it is to just, raise an exception. But as you can see, this other method, raising an exception for each write, is way more expensive than just setting the dirty bit in hardware. So we can do it in OS, but it's just more expensive. What about access bit? Do I really need it in page table entry? Again, as a theme, the answer is no, I don't really need it. I can emulate it. And the way to emulate it is just go another step. So with writing, we gave all pages read only. With reading, we can just make all pages invalid. So even even if the page is really a read, has a read access, we make it invalid. Whenever our process wants to access that page, an exception will be raised, and we can keep track of what pages have been accessed. Again, very expensive, but doable. So when does dirty bit get unset? Whenever you write it back to memory, you can make it unset in your page table entry, and you have to also evict the corresponding translation in your TLB. So if you make the dirty bit, if the operating system unsets the dirty bit, let's say it has written it back to the disk, then you have to evict your TLB. If you keep your TLB, hardware thinks that this page is dirty and it doesn't need to go and tell the operating system. So bad things could happen. So in order to make it consistent, so keep TLB consistent with your page table, you have to evict that that entry from your TLB. That was a good question. Okay. I'm not sure how to pronounce this, but yeah, I'm gonna give it a shot. Homonyms. So what are they? Although I can't pronounce them, I can define them. So the definition is it's a single virtual address that is mapped to different physical addresses. When does this happen? So this easily happens when you have two different processes. All of them are using, let's say, address 0, right, in their virtual address. But then that address could be mapped to different physical addresses. So that's one example where you have a single virtual address that is mapped to different physical addresses. Now, this cannot happen within one process, right? You can't have the same virtual address in your process being mapped to different physical addresses. Because you have the one-to-one mapping in your page table entry. So what's the problem with this? The problem with this is that this could confuse TLB. When you context switch between your processes, and what you have in TLB is basically a virtual page number to physical page number translation. Now when you context switch, you may now use the same virtual addresses, but for a different process. So they might have different physical addresses. So if you keep using what you have in TLB, I'm so sorry, that is actually something that is absolutely invalid. So what should happen? So one thing that you can do is to invalidate all TLB entries every time you context switch. This is very simple, but it's a little bit expensive. What happens if right after you context switch to your new process, you come back to your previous process? Let's say you had a high priority task blocked on IO. You context switch to a lower priority, but then the IO was resolved and the now higher priority comes back. You want to have the TLB entries there again, hopefully. But if you have flushed them, so you have to cache them again, and that's a little bit expensive. So another better way to do this is to tag your TLB entries with the process context identifier. Basically, very similar to tagging it with PID, saying that this translation belongs to this process. So that every time you want to check TLB, you just not only check the virtual address to see if it is cached in TLB, you also check for which process this translation is happening. So I got a question in multiprocessor systems, where two processes can run in parallel. Can you have different virtual addresses mapped to the same physical address? I'm going to talk about that in a second. So it's going to come where different virtual addresses are mapped to the same physical address. I'll talk about it. So hold on to your question. Ask it if I don't address it by the end of this lecture. Okay. Now let's talk about TLB shootdown. Let's say that I have a multi-processor system, and basically in this figure you can see not only I cache the virtual page to physical page, so these are all TLBs. So I have virtual to physical page, and also I have the access bits stored. I also tag it with the process ID. Now, let's say, so remember, we wanted to keep TLBs consistent with page table entries. Now, what happens if, let's say, you want to change the page table entry for process 0, and you want to basically update it. So you want to update the page table entry for process 0, and let's say you're doing it on the processor, on processor 1. So the first thing you have to do, if you remember that slide we talked about consistency, well, the first thing you need to do is to remove the entry that you have for yourself. But as you can see, other processors might also have cached that page table entry. Maybe this process was at some point running on those processors, so its addresses are translated and cached on the TLB of those processors as well. So if you change it now on one processor, you have to make sure that all the other processors also get this update. And the way to do it is you have to send them inter-processor interrupts. So you basically send them a message and ask them to remove their TLB entries, and you wait for all of them to acknowledge before you can move on. This process is called TLB shootdown. You can see that it gets even, it by itself is expensive, and it gets the cost would go up as the number of processors in your system would go up, because you basically need to message all the processors. Okay, let's talk a little bit about what happens if you have a TLB miss. Let's talk about the details. I just mentioned if you have a TLB miss, you're going to do a page table walk. But let's dig a little bit deeper into this. So if you're implementing address translation in hardware, if you have a hardware traversed page tables, if you have a TLB miss, everything so far is fine. You don't need to get the operating system involved. You basically trigger your hardware page table walker to go through the page tables to fill this TLB, which it could take multiple accesses to the memory because of multiple levels of page table. If you eventually find a valid page table entry, nothing really happens. Everything would be transparent from the operating system's point of view, and also the process that is running. So you just fill the TLB and you keep going. However, if you find an invalid page table entry, then at this point you're going to raise the CPU is going to raise a page fault. So you're going to have to make the operating system and the kernel get involved and resolve this page table fault. If you have a software traversed page table, then on any TLB miss, you're going to raise a TLB fault because the hardware doesn't know anything about the page tables, right? So the kernel has to get involved and has to resolve valid or invalid page table entries. And once it's done, it could potentially update the TLB and keep going. So now let's talk a little bit about TLB fault and page table fault, the two things that I mentioned in the previous slide. So if you remember, the difference between interrupts and exceptions was that interrupts are asynchronous. So you're doing your program and then IO interrupts you. It's completely asynchronous. Whereas with exceptions, it's synchronous. So one example is basically the page fault. You access the page that either you didn't have right accesses or for whatever, let's say, you know, copy on write or whatever that field on zero, zero on access or whatever we talked about. So it's because of the access inside your program that the exception rises. So exceptions are synchronous. So when they happen, you have a faulting instruction. So the instruction that caused this exception. Other examples is like, let's say you divide by 0, right? So you have an instruction that caused this exception. What you should usually do is that you have to restart this instruction after you handle the exception, because this instruction didn't go through and it raised an exception. So if the exception is, you know, very severe, then you might actually terminate. But if it's resolved, then you have to go back and restart this instruction. Now, this might sound easy to say, but what if there are side effects in executing the instruction? Let's say the instruction that you're executing is a push instruction, and let's say that where your stack pointer is pointing to is an invalid address. So you have exceeded your stack allocation, and now you're pushing, right? If you remember about pushing, what it does is that you first increase the stack pointer, and then you attempt to write to that location. So now that the page fault happens when you actually write. Now, if you're going to come back and restart this instruction, has the stack pointer been increased? Is it where it was? What happened to the stack pointer? So basically, there's a little bit of, you know, side effect that is a result of executing this faulty instruction, but we don't really know where we are with those side effects. Another example for those of you who are taking the computer architecture course, so in an out of order execution, you sometimes execute instructions out of the order, not sometimes, most of the time, you execute your instructions out of the order of your program. So here is an example. Let's say you are multiplying R2 and R3 and putting the result in R1. And then you're saying branch if R1 is not equal to R4, branch to loop. And then after this, you're loading something to R4. Let's think about this. Let me actually make it a little bit even. Let me make this 5 and 6, so that there's no dependency whatsoever between these instructions. Okay, so now if you have an out of order processor, this branch instruction depends on this multiplication because you're checking the R1, right? And in order to get R1, you need to multiply R2 and R3. Now, this multiplication could be expensive, could take multiple cycles. What you could do, so this branch says if R1 is equal to R4, then go to loop. You might say, okay, I'm waiting for this multiplication. I might want to execute this instruction, right? And then you start executing this instruction. And let's say what you have in R6, and this address is causing a page fault. So in reality, maybe R1 was actually equal to R4, and you had to go to loop. So you would have never executed this load. But because of out of order execution, you ended up executing this load, and it caused page fault. So what should we do at this point? Another example is this one, where you don't have a branch, but you have like a division. You're dividing R2 and R3 and putting it in R1. And right after that, you have a load. So you might say, okay, there is no dependencies between this division and this load, although there is, yeah, let me also change this so that there is no dependency whatsoever, so that we allow the the hardware to execute them out of order. Yeah, so let's say I say, okay, this division takes time. Let me execute this load, and let's say this load actually causes a page fault. What should I do at this point? So these are all examples where it actually shows you that it's not that straightforward, maybe in first sight, to restart your instruction from where the exception happened. Now, luckily for us, these are all taken care of by the hardware implementing precise exceptions. So what the idea, the concept of precise exceptions is that you're going to take care of the instructions. You're going to create this illusion that instructions are being executed according to the order that is given to you by the programmer. And you're going to retire each instruction in the order that is being given to you. So when I'm talking about retiring an instruction, I mean that the instruction will, the result of executing that instruction would be propagated into your architectural state. What is architectural state? It's basically your registers, your memory, and etc., right? Everything that is visible to the programmer. So when I retire an instruction, it means that its result, whatever it is, has been propagated to the architectural state. Now, with precise exception, to implement precise exception, I have to retire instructions with the same sequential order that is specified by the programs. So what that means is exceptions. So what that means is that although I can execute the instructions out of order, I hold on to propagating the result of my execution to the architectural state. So I execute my instructions out of order, and I keep the result in some buffer, let's say, and I don't propagate them to the architectural state until when it's time for this instruction to retire, given the program's sequential order. Now, if I do this, then I can implement exceptions precisely. So when an exception happens, I want to make sure that all the instructions before this instruction that caused exception have retired. And if they haven't, I hold on to that exception until all those instructions retire, then I execute the exception. And for instance, in the case where you had the branch, if it turns out that I have, when the branch instruction retires, if it turns out that I have to go to another address and I don't have to execute the load, I still have been holding on to the exception. I haven't executed the exception. I can just disregard the exception and everything else that the load instruction did, because I shouldn't have executed it at all in the first place. So when indeed an exception is executed, raised by an instruction that is going to retire, so I wait for the instruction to retire, then I raise the exception, so I know that everything before this instruction has been executed and retired. So all I need to do is to disregard everything I've done with the instructions afterward and pretend that none of it has happened. Not this instruction that is the faulting instruction, not any other instruction after this. So I just disregard my executions. If I'm holding to the results in my buffers, I just flush my buffers. I take care of my exception, and then I resume by executing or re-executing the faulting instruction. So here is an example. Let's say the user program is running, then I have a faulting instruction. What you see here is basically the order of retiring of the instructions. So everything before this faulting instruction has retired. Now, at this point, let's say a page fault happens. The operating system gets involved. It fetches the page. It loads the TLB. The loading of the TLB happens with by the hardware, and then you start with your life. So when you're done here, you go back to the faulting instruction, you re-execute it. Let's say you get another instruction here. Again, the same happens. Every time you come back, you execute the faulting instruction. And this all is possible if you have precise exceptions implemented in your hardware. How can we, so okay, TLBs have helped us cache the address translations. That's pretty cool. It's fun. It improves performance. Can I do better? Yes. You can speed this even further. You can have multiple levels of TLB. You don't need to have only one TLB. The same way that we have level 1 cache, level 2 cache, level 1 cache, level 2, and cache level 3. We can have multiple levels of TLB. If you miss in first level TLB, you go to the second level TLB. And let's say that's all you have. Then if you miss in second level TLB, then you have to go and initiate a page walk. So here is another way you can improve. It's called virtually addressed caches. So here is where I'm gonna, so I've already used the concept of caches to speed up translation. Basically, I use TLB as a cache for address translation. Now let's bring in caches to just cache data, right? Use caches as they are for data, not for address. The first thing we can do is we can actually have a cache that is virtually addressed. So all the things that I talked about in this lecture and the previous lecture on caching, what we had was we were addressing our caches, we're tagging our caches using physical address. So those caches are fine, but in order for us to use physical address in our caches, we need to first translate virtual address. And that is a little bit costly, right? So we have to first go to TLB, and if we can't find it, we have to go to page table to get the physical address, and then we can use that physical address to access our cache, our physically addressed cache. So in order to bypass that, we can actually have a virtual cache. So we can have a cache that is addressed by virtual address. So what is this? Why is this helpful? Well, I don't need to translate at all. If I find my data, if I hit in my virtual cache, it means that I have previously cached the data or this location that is addressed by this virtual address. So if I hit, I just get the data and nothing else needs to be done. However, if I miss here, then I have to go through everything that we talked about so far, right? So this basically improves performance another level, right? You bypass all the translation. Well, one thing here is that we're getting really close to the CPU, so this virtual cache is definitely very small, so it doesn't have a lot of capacity. So when it fills up, then you will need to evict it, and you will have to basically go through the translations. The other issue with the virtual caches is basically the issue of synonyms. Let's talk about them. Let me define this. So synonym means you have different virtual addresses mapped to the same physical address. Now, this could happen within the same virtual address space or different virtual address spaces. So you could potentially have two virtual addresses in the same program pointing to the same physical address. And it's easy to see that you can have different virtual addresses in different processes pointing to the same physical address. So in the case where you have two different processes, you can think of when you share a library code. So your library code will be somewhere in your physical memory. So it has a fixed physical memory address. Now, depending on the holds inside the virtual address in process A and process B, each one of them will assign a different range to that code. So you have different virtual addresses pointing to the same physical address. So that's easy when you have two different processes to see this. Now, how can you have this in the same process? So one example of having this, so having basically two different virtual addresses pointing to the same physical address, I have an example, if I have time, I'll show. So it could happen when you use memory map, mmap, to, let's say you have a file. You can map your file. Instead of every time you want to read from your file, instead of using the usual system calls to open the file and then read or write those system calls that we've seen, instead of using those system calls, what you can do to speed up interacting with your file, is to map your file to the memory using this mmap system call. And then once you map your file to memory, you can just load and store to your memory, and load and store to memory will write and read from and to that file, because now that file is mapped somewhere in the memory. So you can basically, by load and store, instead of using system calls, you use usual load and stores to manipulate and read data from your file. I have a question here. So this shared physical page would have to be read-only, right? Not necessarily, right? Let's say two processes are reading and writing from the same file, and both of them have mapped the file to their virtual addresses. So they're both reading and writing to it. If it is code, then probably both of them have access, read-only access. But let's say both of them are working with the same file. So they have mapped it to different regions of their virtual address. Now they can basically read and write from it. But let me finish this one. So let's say if you do this mapping twice. So if you map the same file twice, what will happen is that you will map it twice to two different ranges of your virtual address. But in reality, you have only one copy of it in your physical address. So if you use this mmap twice for the same file, you will get two ranges of virtual memory, but they would both point to the same physical. So that's the definition. Now, what's wrong with it? The problem with synonyms is aliasing. I have a problem today. So basically, with the virtual cache that we talked about, so with virtual cache, we're using virtual address to find our data in our caches. If I have two different virtual address mapped to the same physical address, I may cache it twice because they both have different virtual addresses. And then let's say I write to one of them. How does the cache know that it has to also update the other copy? Because there might be two copies. So that's a problem. One solution, one typical solution that is used is you virtually index your cache, but physically tag it. So if you remember about tags, instead of using bits from your virtual address to tag your data, you can use physical address to tag your data. Now, this is kind of like going against what you wanted in the first place. You wanted in the first place not to have to translate the address. You just wanted to use your virtual address. But if you don't use physical tags, then this aliasing problem will destroy everything. So one way to basically get around this is that you can, in parallel, when you access your virtual cache, you can in parallel access your TLB to translate the address to get the physical address, and then use that physical address to tag your virtual cache. Did I go? Okay. Let me go a little bit further. I know I'm running. I have already run out of time, but a few more minutes. I want to show this example. Now, the synonyms would affect any hardware structure that you have that is dealing with virtual memory. So usually another data structure that is dealing with virtual memory addresses is the store buffer. So if you have a store buffer that uses virtual addresses, then you definitely need to tag it with your physical address. So yeah, so this basically is everything that I said about memory mapped files. Now let me show you an example. This is just an example, so if you want to leave that's you can definitely leave. It will be in the video recordings. So just to show you a piece of code. So here's the code I have. Um, um, okay, so I'm going to get a file name at the beginning, get its size. Then I have this string to write in my file. So here's where the interesting things happen. So at this point, I'm mapping this file. So I first open my file. Very normally using the system calls, I open the file. Let's say read and write. Once I open the file, I'm going to use this FD to map it to my memory. So I use the mem map. I give it the file size. I set the what are the accesses, read and write I'm going to give it. And I say it's going to be shared, so it doesn't really matter at this point. And I'm passing the FD. Now, let's say I do it twice. So this is the example I wanted to show you. Within the one process, I'm mapping different virtual addresses to the same physical address. So I just run the same. So this is just the same code, but I'm using two different addresses. So I basically map my file twice. And then I start writing to one of them. So I use memcpy to write this text to one of them. And at the end, I'm going to just here I'm sleeping. I'm calling a sleep so that I can show you what's happening inside the map. And then I'm releasing it. So let's run this. So here I'm running it with this test.txt. So now it has gone to sleep. Let's look at the so the address for the PID of this task is 10.6.8.2. So let's look at the map for this guy. So this is the virtual address to physical address. So sorry, this is the virtual address space of the process that we have. So as you can see, the stack, this is my code at the beginning of it. These are the shared libraries here. But the interesting one is here. So the same file, this text.txt, has been mapped. If you can see, these are different virtual addresses. So two different virtual address ranges, as you can see here, are mapped, both of them, to the same file. So what happens is the operating system only keeps one. So basically, you only bring the file once to your physical memory. But as you can see, different virtual addresses within the same process are now basically pointing to the same physical address. So if this terminates, you can actually see that if you write using one of the memory maps, it actually writes to the file. Using any of the memory maps, you can just work with your file using the read and write. Okay, so sorry for going over time. I just wanted to show you this example. Yeah, thank you for everyone who participated, attended the lecture. I'll talk to you guys on Monday. Be safe, take care, bye-bye.